What if I told you that the motor in your electric car could basically be shrunk down to the size of a standard dinner plate, but still pack enough punch to completely out-accelerate a top-fuel dragster?
I mean, honestly, if you told me that, I'd say it sounds like some pretty aggressive exaggeration from a PR department.
Right. It sounds totally made up. But, well, welcome to the deep dive, everyone, because today our mission is to decode this radical, really fundamental shift that's happening right now in electric vehicle technology.
Yeah, we are unpacking the rise of the axial flux motor today, which is, it's a fascinating topic.
It really is. And for you listening, we've brought an incredibly dense stack of sources to pull from so we can actually understand the physics here. We're looking at a highly technical academic paper from the University of Nebraska.
We also have the performance specs and some, frankly, wild hype videos from YASA.
Right, the engineering firm that Mercedes-Benz just acquired.
Yeah.
And we've got a beautifully designed Italian engineering presentation on motor cooling.
Plus, a really brilliant, highly skeptical teardown blog post by an electric motor design engineer, a guy named Antia Lehikoinen.
Yes. So to even appreciate why this, dinner plate-sized motor is disrupting the whole industry, we kind of have to establish the baseline, right?
Exactly. For decades, the entire EV industry, and really the broader industrial world as a whole, has relied almost exclusively on what we call radial flux motors.
And visually, if you picture a radial motor, it's cylindrical, like it's elongated.
It's shaped like a sausage, basically.
Like a sausage, right.
Yeah.
So we're essentially looking at why an industry built entirely around these elongated metal sausages is suddenly, like, pivoting to ultra-compact, flat pancakes.
That's a great way to put it, and the Italian presentation visualizes this shift perfectly. These new axial flux designs, the pancakes, they cut the total thickness of the motor by up to 80%.
80%. That is a massive space saving.
Uh-huh.
But the shape change is really just a byproduct of the magnetic topology, isn't it? Like, we need to look at what's actually happening to the electromagnetic fields inside the casing.
Right. So in a standard radial motor, the sausage, the magnetic flux, travels perpendicular to the axis of rotation.
Okay, perpendicular.
Yeah, so the magnetic forces are basically pushing inward and outward, radially, between the spinning rotor and the stationary stator that's wrapped around it.
Okay, so if we think about this mechanically, it's a question of leverage. A radial motor is applying its magnetic force pretty close to the center shaft.
Exactly.
It's a bit like trying to spin a heavy merry-go-round, but you're grabbing the bars right near the center post. You have to exert a tremendous amount of energy to get the thing moving.
You really do. And by contrast, in an axial flux motor, the electromagnetic flux travels parallel to the axis of rotation.
So the magnetic forces are moving side to side.
Yes, side to side, straight down the length of the shaft. And because of this layout, the rotating discs sit face-to-face with the stationary stator. So the magnetic interaction happens at the outer diameter of those discs.
Oh, wow. Okay, so taking the merry-go-round analogy further, the axial motor is like standing on the grass and pushing the merry-go-round from the very outer edge.
Which is so much easier.
Right. You maximize your lever arm, you get substantially more rotational force or torque for the exact same amount of electromagnetic push.
And the underlying geometric advantage of that outer edge leverage is just immense. But here's the thing that often surprises people when they study motor topology.
It's not a new idea, is it?
No, not at all. This isn't some new concept born in a modern Tesla lab. Michael Faraday's very first electrical machine in 1831 was essentially an axial flux design.
1831, that is wild.
And Nikola Tesla even patented a highly detailed disc motor back in 1889.
Okay, wait, I have to stop right there and just look at the timeline. If Faraday and Tesla understood the leverage advantages of this parallel flux over a century ago, why on earth did the industrial world spend the next 100 years standardizing the less efficient radial sausage?
That is the big question, and the answer is that there was a massive showstopper. It came down to mechanical deflection.
Deflection, meaning things bending out of shape.
Right. For any electric motor to operate without just destroying itself, you absolutely need an air gap between the spinning rotor and the stationary stator. They can't touch.
Okay.
But in an axial motor, you have these large, flat metal discs facing each other, and they are generating a terrifying amount of magnetic attraction.
Oh, I see. Because they're flat, wide plates, the magnetic field isn't just trying to spin them, right? It's desperately trying to snap them together, like two magnets on a fridge.
Exactly. And maintaining a microscopic, perfectly uniform air gap across a large spinning disc without the metal bending or warping under that immense attraction.
That sounds like a metallurgical nightmare.
It was. For decades, manufacturing a housing that was rigid enough to keep those plates from crashing into each other, but still light enough to put in a car, it was just economically and physically prohibitive.
So it wasn't a failure of the physics, it was a failure of material science. The manufacturing tolerances back then just couldn't handle the deflection.
Precisely. And the breakthrough that finally solved this wasn't necessarily a structural one, it was actually magnetic.
Oh, really? How so?
The commercialization of super strong rare earth permanent magnets, specifically neodymium magnets. They completely changed the math.
Because they're so much stronger.
Yeah, because these magnets generate such a ferocious field, engineers can design machines with slightly wider, much more forgiving air gaps.
Ah, so you can leave enough physical space to accommodate a tiny bit of deflection without the plates ever making contact.
Right, which suddenly makes mass production viable.
The materials finally caught up with Tesla's blueprints. That is incredible. Which I guess brings us to the modern specs from YASA,
Yes, the YASA numbers.
because their prototype numbers claim a peak power density of 59 kilowatts per kilogram, which to me seems almost entirely detached from reality.
It is a truly staggering metric.
I mean, for context for you listening, a standard EV motor right now might hit, what, 15 to 20 kilowatts per kilogram?
Yeah, around there.
And a top fuel nitromethane dragster is putting out roughly 30 kilowatts per kilogram. So YASA claiming 59 requires a fundamental reimagining of how much power you can extract from a specific volume of mass.
And that 59 number is exactly what triggered Antal Lehikoinen's teardown. As an electric motor design engineer, he looked at 59 kilowatts per kilogram and felt it was just perplexingly high.
Like he thought they were lying.
Pretty much. So rather than just taking the marketing materials at face value, he decided to reverse engineer YASA's entire design through rigorous software simulation.
And they call it a yokeless and segmented armature, right? That's what YASA stands for. A lot of the online discussions focus really heavily on that yokeless aspect.
I do, yeah.
The assumption is that simply deleting the heavy iron backing yoke that you find in radial stators removes so much dead weight that the power-to-weight ratio just naturally skyrockets.
Which makes sense on the surface. But Anatoly addresses that assumption directly. He breaks down why weight reduction is really only a fraction of the story.
So taking the iron out helps, but it's not the magic bullet.
Right. It helps, certainly. But the true defining benefit of YASA's topology is how it circumvents the geometric scaling penalty.
The geometric scaling penalty. Let's unpack the physics of that. In a traditional radial cylinder, if an engineer wants to increase the power output, they need to increase the electric loading, right?
Exactly. And to do that, you have to pack more copper wire into the stator.
But since you're constrained by the outer casing of the motor, the only way to fit more copper is to dig deeper slots into the iron core,
Moving toward the center, yes.
which creates a vicious cycle. By digging deeper slots toward the center shaft, you're actively shrinking the inner diameter of the air gap.
You're literally reducing your rotor size to make room for the copper.
Wow. So going back to our merry-go-round analogy, you're basically forcing yourself to push closer and closer to the center post. You are cannibalizing your own mechanical leverage just to fit the wiring.
Exactly. You're trapped by the geometry of the circle. You trade torque for copper, but in an axial motor, the geometry works with you. If you want to increase the electric loading in an axial motor, you simply deepen the slots along the axis. The magnetic air gap diameter doesn't change at all. The motor just gets like a few millimeters longer.
Oh, I see. So there is zero geometric penalty for adding copper.
None. You maintain your maximum outer edge leverage while drastically increasing the magnetic field strength.
Okay, that lack of a scaling penalty really explains the foundation of the power output.
Yeah.
But YASA implements another specific architectural choice that Anieti highlighted in his blog, right?
Yes, the dual rotor configuration. They sandwich a single stationary stator between two spinning rotors.
The ice cream sandwich model.
Exactly. And that configuration is often referred to in the industry as the YASA trick, because the magnetic flux flows actually straight through the stator core. Utilizing both sides of the stator essentially splits the machine in two.
Wait, splits it in two?
Yeah, you have the required electric loading per air gap. That keeps the inductance low and the efficiency super high, while still compounding the torque from both rotors at the same time.
But wait, looking closely at Anti's reverse engineering data, there's a discrepancy that really stands out to me.
Oh, the 250 kilowatt limit.
Yes. When he simulated that specific configuration, one stator sandwiched between two rotors, he pushed the simulated current absolutely as high as the software model could tolerate. And the resulting power output capped at 250 kilowatts.
Yep.
But Yassi's documentation claims 750 kilowatts total to hit their 59 kilowatts per kilogram power-to-weight ratio. A single stage falls short by a factor of 3. Did Yassi lie?
They didn't lie, but Anti ran headfirst into the ceiling of what we call magnetic saturation.
Magnetic saturation, what is that?
Basically, the steel laminations inside the core can only carry a finite amount of magnetic flux before they become fully saturated.
Like a sponge that can't hold any more water.
Exactly like that. Once you hit that threshold, pumping more current into the copper coils doesn't generate any more magnetic force. It just creates massive amounts of waste heat. The metal physically cannot hold any more magnetism.
So if the physics of magnetic saturation prevent a single stage from exceeding 250 kilowatts, the only way Yassi achieves 750 kilowatts is, well, how do they do it?
Modularity.
Modularity.
Because the magnetic flux moves linearly parallel to the shaft, you aren't forced to redesign a completely new, larger motor. You just stack multiple independent stages on the exact same shaft.
Oh, like adding more patties to a sandwich.
Exactly. And Daci realized you can stack multiple yokeless stators and rotors back to back. His simulation proved that by chaining 3 of these modules together on a single shaft, you easily hit that 750 kilowatt target.
Creating a multi-layer burger of immense torque.
It really is. And because each stage is so incredibly thin, a 3-stage axial motor is still dramatically more compact than a single-stage radial motor of equivalent power.
It's a remarkably elegant solution. But it immediately creates a secondary problem, doesn't it? Because running that kind of current through tightly packed copper coils to generate 750 kilowatts in a space the size of a few dinner plates.
It creates a thermal monster.
Right. Heat is the absolute bottleneck of all electrical engineering.
And to reach that record-breaking power density, Anti's calculations showed the current density had to hit 90 amps per square millimeter.
90 amps. And Kathy dryly referred to this in his blog as trying to cram 90 elephants into a space meant for one.
It's absurd. The specific heat capacity of copper makes that number completely terrifying.
Yeah, if you push 90 amps per square millimeter through those coils without aggressive thermal management, what happens?
Well, the energy dumped into the winding resistance would cause the temperature of the copper to rise by 30 degrees Celsius every single second.
Every single second.
Yep. The insulation on the windings would vaporize, and the motor would literally melt into a block of slag in under a minute.
Wow. Okay, so how do they fix it?
Yeah.
Because the Italian engineering presentation we reviewed details exactly how this thermal bottleneck is solved, and it requires abandoning traditional EV cooling entirely.
Right. In a standard radial motor, cooling is usually indirect. You basically wrap a water glycol cooling jacket around the outer iron casing of the stator.
So indirect cooling relies on thermal conduction. The heat has to slowly migrate from the copper wire, fight its way through the electrical insulation, pass through the iron core, and then finally reach the coolant jacket.
It's a very slow, highly resistant thermal path.
Way too slow for 90 elephants per square millimeter.
Way too slow. So the Italian presentation shows that Yassi utilizes direct oil cooling, specifically a technique called jet impingement.
Jet impingement, that sounds aggressive.
It is. Instead of waiting for the heat to conduct soapward, they inject dielectric cooling oil directly into the core of the stator. They are aggressively spraying it right onto the bare copper end windings.
So the oil physically bathes the copper.
Exactly. By directly targeting the primary heat source, you drastically lower the thermal resistance of the entire system. The heat is wicked away the instant it's generated.
And the real-world application of jet impingement, it kind of changes the entire paradigm of how we drive electric vehicles, doesn't it?
Oh, absolutely. If you take a standard performance EV to a track day, or if you're simply doing repeated heavy accelerations on the highway, the copper windings heat up rapidly.
And as the temperature rises, the electrical resistance of the copper increases.
Right. And to prevent catastrophic failure, the vehicle's computer intervenes through a process called derating.
Derating, where the computer artificially throttles your current to save the motor.
Exactly. So a motor rated for a peak of 200 kilowatts might suddenly restrict you to 80 or 100 kilowatts until the system cools down.
Your performance degrades exactly when you were asking the most of it.
It's super frustrating. But according to the cooling data, jet impingement eliminates this fade almost entirely. A 200 kilowatt Yassi motor can run continuously at 150 kilowatts.
That's maintaining 75% of its absolute peak power.
Yes, all day long, without fading.
And the Italian presentation provides the ultimate proof of concept for this, don't they?
Yeah.
Mercedes-Benz integrated this specific motor technology into their AMG GT XX prototype.
And then they deployed it to the Nardo high-speed test track in Italy, which is notoriously brutal on powertrains.
Right. For those who don't know, the Nardo Ring is a 12.5-kilometer continuous banked circle designed for sustained maximum velocity.
They ran the prototype for over 40,000 kilometers over the course of just 8 days.
That is wild.
It gets better. The vehicle maintained cruising speeds of 300 kilometers per hour in 35 degrees Celsius ambient heat.
So sustaining 300 kilometers per hour in almost 100-degree Fahrenheit heat, with minimal downtime because they used ultra-fast charging to keep it on the track nearly 24 hours a day.
It's an absolute torture test for stator insulation, and the telemetry data showed zero thermal degradation.
Zero.
Zero. The stator and the rotors remained entirely locked within their optimal thermal operating windows, entirely due to the efficiency of the direct oil cooling.
That is just incredible. Now, the ability to sustain those loads in such a compact package naturally means the first commercial applications are dominating the ultra-premium sector.
Oh, yeah. Right now, we are very much witnessing a supercar pioneer phase.
Right. Ferrari is relying on these axial designs in both the SF90 and the 296 GTB. McLaren utilizes them in the Artura.
And from a vehicle architecture standpoint, the packaging flexibility these motors offer is just unprecedented.
Because the axial motor is 50% lighter and requires only 20% of the longitudinal space of a radial equivalent.
Exactly. Ferrari engineers literally slide this tiny pancake motor straight into the existing gap between the V8 internal combustion engine and the transmission bell housing.
They seamlessly integrate hundreds of horsepower of electric hybrid boost without having to lengthen the wheelbase at all or alter the complex suspension geometry.
It acts almost like an oversized, highly active clutch plate. It solves the packaging dilemma that has plagued hybrid sports cars for 2 decades.
But, viewing this solely through the lens of hypercars is kind of a mistake, I think.
Yeah.
Because the academic paper from the University of Nebraska highlights a commercial pivot that demonstrates the true scalability of this tech.
Yes. That section of the paper completely reframes the whole narrative.
It does. Fasco Australia is currently mass-producing a 900-watt, single-sided axial flux motor. And it's not for a supercar hybrid system.
No, it's for swimming pool filtration pumps.
Pool pumps. Transitioning from Nardo track dominance to suburban backyard pool pumps, that requires examining a massive disruption in manufacturing economics. How are they doing that?
Well, high-performance radial motors are typically manufactured using progressive die stamping. You take massive sheets of highly specialized electrical steel, and you use incredibly expensive machinery to punch out the complex circular laminations that make up the stator core.
But there's an inherent flaw in stamping circular components out of square steel sheets, right?
The scrap rate. You end up wasting a staggering percentage of premium expensive steel, and the progressive die machines themselves represent a massive capital expenditure.
So what did Fasco do differently?
Fasco analyzed the axial flux topology and realized it allows for a completely different manufacturing process. Because the axial core can essentially be a continuous ring, they employ a numerically controlled punch-and-wind machine.
A punch-and-wind machine.
Yeah. So instead of stamping circles out of sheets, they take a single continuous ribbon of steel. The machine punches the necessary slots for the copper wire into the ribbon, and then it just tightly coils that ribbon upon itself like a roll of tape to form the stator core.
Like a roll of tape. So the only steel wasted in that entire process is just the tiny rectangular chips punched out for the slots.
Exactly. The material efficiency approaches 100%. It utilizes cheap machinery, generates minimal waste, and the resulting pool pump motor is so compact that the integrated electronic controller physically takes up more space than the motor itself.
That is amazing. It replaces these bulky, inefficient induction motors with something vastly superior at a lower price point. We have really tracked a phenomenal engineering trajectory today.
We really have.
I mean, we started with Michael Faraday's early designs, which were limited by the deflection nightmare of 19th century metallurgy. We explored how neodymium magnets unlocked the geometry, allowing YASA to bypass the scaling penalties.
We looked at the jet impingement cooling, taming the heat of all those copper elephants.
Right, enabling Nardo track dominance. And finally, how punch-and-wind manufacturing actually democratizes the entire concept for mass adoption.
The technology adoption curve is moving exponentially,
Yeah.
but integrating these motors into transmissions or pool pumps is really just an intermediate step.
Oh, really? There's another step.
Oh, yeah. The ultimate, highly provocative endgame for the automotive industry regarding axial flux technology is full in-wheel integration.
In-wheel integration. Wait, Because the motor profile has been reduced to the size and shape of a dinner plate, there's no longer a physical requirement to keep the powertrain centralized under the hood.
Exactly. The entire drive unit can be mounted directly inside the hub of the wheel itself.
Wow. From an engineering perspective, that eliminates immense amounts of parasitic mechanical drag. You
Right.
completely delete the transmission, the drive shaft, the differential, the hash
You
shafts.
deliver the torque directly at the point of contact with the road.
And if you push the implications of in-wheel motors to their logical conclusion, it fundamentally alters what a car actually is. If the whole mechanical drivetrain is housed within the four wheels, the vehicle chassis becomes completely empty.
Think about the crash safety structures. Without a massive rigid engine block sitting up front, engineers can completely reimagine crumple zones. You no longer have to design around preventing a solid block of metal from being driven into the passenger cabin.
It frees up the entire chassis for batteries or radically spacious cabin. The volumetric efficiency just transforms. You could shrink the exterior footprint for dense urban environments while expanding the interior space.
It's a total paradigm shift in urban mobility and industrial design.
And it is entirely dictated by a decision to pivot the direction of the electromagnetic flux 90 degrees. We are truly transitioning from the era of the cylinder to the era of the disc, and the ripple effects will reshape the infrastructure of how we move.
It's going to be wild to watch it unfold.
It really is. We want to sincerely thank you, the listener, for joining us on this incredibly technical journey today. Exploring the mechanical realities behind the electric revolution is only possible because of your dedication to digging deeper than the surface-level marketing hype.
The boundaries of engineering are rarely absolute, you know? They are usually just waiting for a shift in perspective.
Beautifully said. Keep scrutinizing the machines around you. Keep demanding to know how the physics actually work, and keep questioning the limits of what is possible. Until next time, stay deeply curious.